once again, thank you a lot for being here with us, and please feel free to start whenever you're ready.
Okay, let me share the correct screen. Okay, so 1 second. Let me just make sure my notifications on the laptop don't pop up. I didn't think about that. Okay, okay. Do you guys see it in presentation
Yeah, perfectly.
now?
Yes.
Okay, good. Okay, so today I'm going to speak about Icicle. Icicle is a CUDA library that we're developing in-house at Ingonyama. It implements different cryptographic primitives. So we implement like points, fields, MSM, NTT, and many other primitives that build up these cryptographic systems. Um, so whoever doesn't like, I'm not sure how many people here heard of Ingonyama, but we're a hardware acceleration company, and we focus on research and development of hardware acceleration for zero knowledge proofs, and but also for encryption in general, so for FHE as well. Our designs are built around GPUs, FPGAs, and we're also working on a ZPU, a zero knowledge processing unit, which is supposed to be basically a similar to a GPU, but like a dedicated hardware that will be designed for accelerating ZK applications specifically. Um, okay, okay, so what is Icicle? I already said that at the beginning, but it's a CUDA library for GPU acceleration of ZK primitives. Um, so like Icicle is built up, we try to build it in a component-based way. So we have a bunch of APIs that can be used separately. We have MSM, NTT, we have uh, different polynomial functions, field functions, group functions. We support Poseidon hash. We also have a system for supporting multiple curves and allowing developers to add their own curves. Um, yes. Oh, and if anyone has any questions, feel free to alert me. I don't know exactly if I'll see if you raise your hand in the chat, so you can also interrupt me mid-sentence.
Okay, awesome.
So why are we building Icicle? Well, what we realized is that most most ZK algorithms and ZK provers in general, they were running on CPU. Just because I think the like reason for that was because most of these systems are very cutting edge, and it's just uh, pretty easy to write them on CPU. It doesn't require any special knowledge. Um, Now we believe at Ingonyama that GPUs are the prime hardware at this current time for ZK for a couple reasons. One is because GPUs are cheap and everyone has them almost. Like it's very easy to get GPUs. And two, it's actually incredibly easy to develop on GPUs. Developing for ASICs is way more complex. It requires like there's no easy framework or easy way to actually integrate an ASIC into your code. It requires a lot of very low level work and development. Um, and also the results of the Z Prize have shown that MSM and NTT can be significantly accelerated using GPUs. I think it's also important to note that GPUs can scale pretty rapidly. Like the idea of a GPU cluster is pretty prevalent from AI, and the same can be applied to ZK. Um, yeah, so these are some of the points that I covered about why GPUs. So in order to illustrate how to use Icicle and uh, the benefits that Icicle can give you as a ZK developer, we will go into an integration that we did between the GNARC prover and the Icicle library. This was a official collaboration between between the Gnark team and Ingonyama. Uh, so I will begin by covering some concepts that I think are important to understand how to integrate Icicle into an existing code base, or even how to write a completely new code base from scratch with Icicle. So when you have a machine with a CPU and a GPU, you have RAM, and then you also have GPU RAM or GPU memory. So you have host, which is CPU, and you have the GPU, which is the device. And you have to move memory between these two devices. So lots of times you'll find yourself, let's say, getting some scalars or some points on host on the CPU, and you have to copy it over to the GPU. This operation can take time. For very, very large circuits, it can even be seconds to actually copy data. So when you're designing your GPU accelerated software, you need to keep this latency in mind. The optimal strategy is to copy as much data as you can initially from the host, from the CPU to the GPU, do as many computations as possible on the GPU, and then only copy the result back to the CPU. That is like, I guess, the like optimal strategy uh, for writing GPU software. Um, so in this integration, we accelerated uh, two main primitives. One is MSM, which is multi-scalar multiplication, and the other one is NTT and INTT. If you guys are familiar with the low levels of Graph16 or if most of these provers, these are two of the main primitives that take up a lot of the runtime during computation. Um, I I will go over. I explained what Gnark was at the beginning, but here you can actually read the like Gnark code base. It's a Golang prover. It's designed by Consensus, but they have their own development team. Uh, named the like Gnark team. So this is the high level integration architecture. So we have the like host or the CPU running the Gnark prover, and it's integrated with the Go Icicle, which is a Golang binding for Icicle, and it has Gnark Crypto, which Gnark Crypto is the library that we're replacing with Go Icicle. So Gnark Crypto also implements MSM NTT, but it implements it on CPU. Go Icicle implements the same thing on GPU. So you can think of Icicle as like this package that contains some CPU code, like bindings basically, and then you have this CUDA code, these CUDA kernels, which each kernel implements a different primitive, like MSM, NTT. So this is like the high-level architecture of the integration. Now we'll go a bit deeper into the details. So at the first stage, you want to research the algorithm that you're going to actually accelerate. Here we created this graph describing most of the stages of graph 16. So here you see we have, I don't know if it's too small to see, but if okay, if I zoom in, I don't know if that helped, but you have like MSMs here. Here you have FFTs, NTTs. Um, and then here you have this function named the H function, which we'll also touch on in a moment. Yeah, so these are arrows just to illustrate the different points of where we're going to actually accelerate. Here you can actually go to the code and see the actual code base, but we'll go over it. So, like I said, in an optimal GPU implementation, you'll want to first of all copy most of the data or all of the data to the GPU before doing any processing. So during the setup phase, this is the phase where it's a Graph16 Gnark implementation. They will actually like pre-compute some values. They will get like the like scalars and the points needed for the actual proof generation. So we use this stage to not only generate all of these different data points, but we also load them onto GPU. So if you see where my cursor is here, we have this function named go icicle CUDA mem copy host to device. So this function, for example, uh, it basically copies some data. It can be scalars or points, and it or really anything basically, but it copies it from the host to the device. So you see, we do that for like scalars, and we do that for the like G1 points. So we basically load everything into the GPU before we even begin generating any proof. Okay, so if I go back to this graph, that would be like this phase. Like this this diagram doesn't show the entire flow, but you have up here the setup phase. Okay, and now we enter step one. So step one, we're gonna accelerate MSM. So here as well, I want to illustrate how easy it is to actually use um, Icicle. So this is the original Gnart code. So you see we have the original multi-exponent function right here. We literally just had to replace it with our function MSM on device. This is a Icicle function. And we pass into it the pointers to the values that we copied onto the GPU during the setup phase. So you could like what's really happening here is we copied the data into the GPU, and now some parts of the prover are running on the CPU, but all of the heavy computation is running on the GPU. And you're just passing in pointers now. You're not even passing in the actual data. You're just instructing the GPU to initiate some kernel, and that kernel should take these these pointers to read data from and process. Um, Now, do you remember I was speaking about the like H function? So the H function shows us an interesting challenge. So we have here these three FFTs. Then we have here this H function, and then we have this IFFT. Now, if Icicle only implemented FFT, you would need to compute this on GPU, copy it back to CPU, compute this on CPU, and then send it to GPU again. This would actually hurt performance tremendously, especially for very, very large circuits. So here I'm going to demonstrate how we actually use Icicle to implement this entire algorithm, this entire flow on GPU. So here's the the original Gnart code. So as you see on CPU, every FFT happens sequentially. So you run like the, this one FFT, another FFT, then you have these other FFTs running down here. You compute compute H function in a parallel, and then you do this other FFT here. However, here what we did is using Go routines, which is like multi-threading for Golang, or like concurrent multi-threading for Golang. We actually launched these INTTs and entities in pairs. So we would launch them in pairs and we would run them in parallel on the GPU. So instead of it happening sequentially, these entities slash FFTs are occurring in parallel, in pairs on the GPU. We then implemented this function named polyops that utilizes some of Icicle's polynomial operation library. We basically implemented this parallel multiplication algorithm here on the GPU, and then we called the final INTT or inverse FFT. Okay, now it's important to note that all of this occurs on the GPU, so we avoided any need to copy data back to the CPU. Okay, the results of this. Okay, so we benchmarked this on a 2 to the power of 23 um, circuit. We benchmarked it on a couple different platforms using different CPUs, different GPUs. Um, these are the general proving times with each one of these setups, but I'll show you a better illustration of the actual speedups. So NTTs, we have a 15x speedup. The H poly algorithm, the like H function here, was sped up times 9, MSMs times 4. The total prover was times 5. Now, one important thing about MSMs, um, you see, so MSMs, we actually didn't run them in parallel on the GPU. They are still executed sequentially. The reason for this is because at the time of this integration, we didn't support multi GPUs. And the MSMs on large circuit sizes actually consume a huge amount of RAM, of GPU RAM. So we found that it's actually only worth running one MSM per GPU. I think we had like a 24 gigabyte GPU. But now that that we support multi GPUs, we can actually run MSMs in parallel on different GPUs. So this MSM acceleration can actually be scaled with more GPUs or if GPUs with more RAM. Yeah, so these are I guess like more granular uh, benchmarks showing how on a high-end CPU versus a high-end GPU, we were able to accelerate individual NTTs slash FFTs. Um, the polyops you see from 48 milliseconds down to 2. MSMs as well. We were able to accelerate. Yeah. So here are some resources to get started with Icicle. Yeah, this was 1 second. What was that? There was some alarm. What like I don't know what that was. It was an alarm. Um, yeah. So I think if anyone has questions about this part of the lecture, I'm happy to answer. If not, I can go into I can go over the like Icicle code base and go over like some of the details about how to use Icicle.
Will there ever be time when we could maybe generate proofs using our phones? Or what do you think?
Um, so yes, I mean phones have GPUs. The thing is that Icicle won't work on a phone GPU because it's written in CUDA. Um, so for example, I'm not sure about iPhone. Let's take iPhones or Snap or like Snapdragon GPUs on uh on on Samsung phones. I'm not sure exactly like um what like if or when Icicle is going to support these devices. But there's definitely room for using mobile GPUs to accelerate ZK. The only issue is that large circuits they require a lot of RAM. So, for example, I'm not an expert on phone GPUs. I don't think they have a lot of RAM. I'm guessing they have like 8 GB of RAM. So I'm not sure exactly about the like in the near future if that will be possible to use the GPU on your mobile device.
All right, thanks for doing this. This is super cool. Can you hear me?
Yeah, I can hear you.
Awesome. So I guess my first question is, so some circuits might use different gadgets. For instance, like there's been a lot of like work over the last 2 months have shown like lookups and like using protocols that can like cache certain like computations beforehand and then use like a lookup table to prove, or well, in the prover computation can be like super efficient. So I guess one question I have to ask is like, um, how does like Icicle perform with like gadgets that are
You,
like kind of different circuit from circuit?
your last sentence cut off.
I'm just curious, like, how does like performance in Icicle depend upon like the type of circuit you're running and like different gadgets that you use? For instance, like a lookup, a circuit that has a lookup, it's going to be like a lot more memory intensive because you have to store all like the lookups in it. Have you guys like seen any difference between that?
Yeah. So speaking about gadgets, you're probably speaking about Halo 2, right?
Yeah, along that lines is what I kind
Yeah.
of experiencing.
Yeah. So Gnark integration was only Graph 16. So integration was only for Graph 16. However, we're currently working on well, actually, we're currently working on this direction for Halo 2, and we're working on a Halo 2 integration with the like for the actual official like PSC version of Halo 2. Uh, so I can't really say anything about that now, but we'll have a blog post about this, about like caching and how GPUs compare and how like Icicle can work with these types of systems. But I don't have any benchmarks to tell you like some number right at this point in time, unfortunately.
No problem. I guess my next question was just how like memory intensive like does this get like in the systems you guys are running on? Obviously, you're doing this in a box on a server, but like, what are like the? I understand there has to be like a lot of GPU RAM available, but like as far as like the CPU side, like, is there any like difference, or are you still having to like have a ridiculous amount of RAM on board to run these proofs in addition to like running it with a ridiculous amount of GPU RAM?
Yeah, so currently we're benchmarking it on RTX 4080 and 4090 GPUs. Um, we've like some people that were integrating Icicle found that, for example, GPUs of like if they're working with 2 to the power of 23 circuits or more, uh, you need at least like 16 gigabytes of RAM, probably like 24 gigabytes of RAM. So it's very intensive on memory for large circuits. Um, Now, when it comes to CPU, the current Gnark implementation is very GPU oriented. So I mean, yes, you have to generate, like we generate the points and we generate effering on GPU. We wrote functions to generate scalars, generate points, effering on GPU. However, we do think that there's room for like heterogeneous computing. So, for example, like while the GPU is working, the CPU could also be doing some other work. So we're still experimenting with like hybrid acceleration, I guess, between like CPU and GPU and how they can work together. Um, yeah, this is also like it's a work in progress. I because like the answer I guess is that like right now it's very memory intensive for large circuits, and the systems need to be pretty beefy. Yeah.
Um, maybe I guess like another question I have with this is like correct me if I'm wrong, but like isn't Gnark and like Ground 16 have I forget I don't know off the top of my head if they have an SRS or anything like that. I'm sorry, this is a pretty embarrassing thing to admit.
Uh,
But one thing that like becomes a concern of like some proof systems is just you have a huge SRS that if you want to run a proof or do anything with, you have to like download this huge like file. I guess have you guys like keeping in mind this is so like GPU intensive, has that like informed your guys' decision making or anything? Or have you guys like
yeah,
thinking about this at this stage? I'm
yeah,
just thinking along as like Aleo has like this huge file that you need if you want to run a prover, and it's just kind of ridiculous. So
yeah.
I wanted your thoughts or anything like that.
Yeah, this is actually on our roadmap. The witness generation. So we want to accelerate the generation as well. So developers, for example, especially if like trusted setups, won't have to generate their witness like each time, and like sometimes you have to wait multiple minutes for it. So yeah, like we want to accelerate the like setup phase as well for developers.
Okay. Does anyone else have a question? I got some more. I don't want to like take over. Like if anyone else wants to say anything, I don't want to get in the way. Okay. Um, I get one more question I have is do you guys have plans in any way to like kind of adapt this to be working in like a more distributed setting? Do you guys think that would be viable in the future?
Yeah,
Uh,
yeah,
I'm just kind of curious because like this is all assuming that you're running the same box in the same machine. But like it sounds like very attractive to me to be able to like, as you would to run an ML model like Google, um, what is it called?
like a data center
Yeah,
style.
yeah, or something like that. Like, I have my CPU running. I have my local machine, but then I can just offload stuff onto the GPU cluster, like you would on like an ML model or something like that.
Yeah, yeah. So this is what we're working on now as well. We added multi GPU support on this. There's this branch under Icicle called multi GPU. It has multi GPU support, and we also have a team working on there's like virtualization, so you can like scale Icicle to GPU clusters. So for example, let's say that you're some I don't know like Alio miner and you want to do like GPU ZK mining, or maybe you're an Alio wallet, right? And you want to like host proof generation for your clients, right? Then and you need to generate like massive amounts of proofs. Then we're developing this type of solution. Yeah, and everything that we do is also open source. So Icicle's open source. Everything's going to be is going to be open source. So you could experiment with these tools as well.
Awesome. Thank you very much. This has been like super interesting so far.
Yeah. Um, oh, and like one more point. Also, we're working on like really thorough documentation. I was actually going to. How do I reshare my screen? 1 second. I wanted to show you guys this some of the some of the code. Okay, how do I share my 1 second? Okay. Yeah. So currently, like, if you clone Icicle, we have some documentation on how to actually use it here. So uh, let me just go over it really fast to give you guys a feeling of what you can do. So currently we have two bindings. We have the Go Icicle bindings, which are Golang bindings, and we have Rust bindings. So this lets you just like call functions in Golang or in Rust. I'll show you some example, like in some test, what this would look like. So let's say that you want to call MSM. You see, you would just import. Second. Yeah, you would just import like MSM here, like this function, and it's basically a wrapper for the CUDA. So you see, like we use CGO to we first like compile the like CUDA libraries, and then we use CGO to basically call these CUDA libraries from Golang. Same thing exactly with Rust. So if you're a developer and you want to integrate this into one of your programs, currently you can do it with Golang and Rust. It's actually pretty easy to do this with Python as well. So if someone wants to add those bindings. Another interesting feature that we have is adding curves. So supporting additional curves. Currently, the curves that we support out of the box are BN254, BLS 12381, and BLS 12377, and BW67. But if you want, you can just add under curve parameters. You look up these different parameters. They're available. They're available almost in every curve white paper. These different parameters, and then you have the script. This script will generate for you all of the Golang and all of the Rust files and all the CUDA files required to support a curve. So you can basically add any curve that you want, generate it, compile it, and then use it in Golang or in Rust. We also document how to actually compile everything here. So this is for the like Golang library. We have this make file. So you would just like, for example, you would just call like you would just go to like go icicle, and then you do make, and then you would put the name of the curve that you want to build. So here it's BN254, and this would build for you this shared library. So if you see here, there's this shared library like here, lib BW67. So this is a shared library for the BW67 curve. And then you would be able to call this shared library from Go Icicle bindings. Um, yeah, under Icicle, here is most of the CUDA code. So here, here's like curve specific code. These are like the general MSM, NTT, Poseidon hash, vector functions. And then we have different primitives. So like the fields, the points. Um, yeah, I think I think that's that's basically all of the main points to get started with Icicle. And again, we're gonna have like very thorough documentation coming out in the next couple days. Um, everything is open source. We also have a Discord channel, and you can ask there any questions that you want, or just open an issue on GitHub. We love answering questions and helping people use Icicle. Yeah. So if there's any more questions, this is also a good time.
Any questions or something? We really liked Icicle a lot. We have it in our roadmap to include it in our library so that anyone can, when using Lambda works, can then leverage all the advantages of Icicle. But well, we are still like finishing some things related to the start prover, and so we kept a little bit postponing it. But I think now it's like a good time to, as part of the bootcamp, maybe to try to make this inclusion. Um, and something I wanted to ask you is regarding Poseidon acceleration, because we know that Poseidon is a more convenient hash function for snarks because it's arithmetization friendly, but we know it's much slower than ordinary hash functions like Ketchak or Blake 3. So I don't know if you have like any numbers or any idea of how much you can speed up Poseidon, because that could like be a massive boost for example, Starks.
Yeah. Um, I don't have any numbers on me. However, I'll ask our developer working on Poseidon, and I can send you the actual speed up that he recorded, and and then you can share it with everyone. I think.
Okay.
I Fortunately, like reason that I don't have numbers is because like currently like the I guess like flagship integration was in Graph 16. So we didn't have any measurements like in production measurements, I guess, for Poseidon. But I'll get back to you with numbers about this.
Awesome, thanks. So please, Pat, use the microphone directly.
Oh, sorry. I just had a question. So for you guys' MSM implementation, do you guys have curve specific optimizations? For instance, like in some pairing-based curves like BLS 312381, you can actually like speed up the Pippinger by doing like by efficiently computing these endomorphisms during runtime. I was wondering, like, do you guys have optimizations like that currently in your MSM implementation?
No, I don't think so. Our MSM is based off this research paper from Ingonyama. I'll link it. Let me link it here. But no, not no. I don't think that we have such implementations. I mean, such optimizations in our MSM. implementation. But let me send you the actual paper for it here. Yeah. Like, oh,
Awesome. Um, yeah, I really like the docs. Uh, they help you learn like many cool tricks. I always enjoy them. Um, we are also like right now starting our Growth 16 implementation. So maybe we can, of course, try to use Icicle from scratch.
yeah.
Going to be in Rust, so I think it will be nice like to have a test with the Rust bindings and see how it works in the case of our library. Um,
That'd be great.
any other questions? Something you're interested in?
I'll send you guys the PR, the official PR for the Gnark uh, integration, so here you guys can like go over the actual code for the integration in more detail.
Ooh, that's awesome.
Yeah.
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 Anything else? So I guess that I don't know in in case of Rust, I think that you used like artworks for finite fields or something. If I am,
Yeah, so we didn't use artworks for finite fields. We used artworks for correction at the
Mhm.
beginning. So like we actually have a PR to remove artworks, but when we initially started to develop it, we needed to test correctness, right? So we used Gnark Crypto for the Golang libraries and for the test, and we used um, arcworks for the Rust binding. So like initially we didn't have function, we didn't expose the functions to generate points, to generate random points, and stuff like that. Um, yeah, but now we also have all these functions, so you can generate your own points and all these like other functions.
Awesome. Um, any questions? Um, well then, we were like really happy to have you here and explain things about the library. I think the work by Ingonyama is awesome. We always enjoy doing things with you, and so we were pleased to have you here in the bootcamp. We will be co-hosting something in Istanbul next November.